So, I hope you are okay. This is last 2 weeks of semester, and this week will be our last lecture week, right? Because next Monday we'll finish on Wednesday, and then we will have a review section on Monday, and then we have the final exam on next Wednesday, right? The next Wednesdays will be in the central campus. And we've seen that in the course website where we are. So it's open book. So as probably you know that the last is the regression. As I have mentioned last class, this is one of the most important chapters in our course. And if you want to do a second class in analyze based on data, that will be an extension of all the regression models. I mean, we focus on the very simple case we call simple linear regression. Simple means only use X to explain Y. So the standard case is more than one, right? It's actually everything can be generalized to more than one easily. There's some more math, but ideally everything is the same. Okay? There's some more complication there, but the general concept will be the same. Okay, it just instead of drawing a line, you draw a plane, right? If X and Y and Z, then it's a 3D graph is a plane, right? If more than 2 dimensions, then it's like a 3D, it's like a hyperplane. It's like you can't think about it, but the idea is similar. Okay, you can't think about it geometrically, but that everything is like fitting a plane, okay, in a higher dimensional space. And we have a linear regression, right? So you can do extend to non-linear, okay, but that will be beyond the scope of what we're doing, okay. But you will see if you want to do further, that will be the thing, right? And I also mentioned that regression is probably you would say the very first machine learning approach, right? I mean, if you learn later when you go to the machine learning classes, you see regression is the very first model that you learn, right? Then you go to regression tree, say random forest, more stuff, but that would be the very first thing that you will learn. Okay, but that being said, let's go ahead. But regression is something that we try to explain looking at in our model, is just look at 2 variables, right? Say look at how education and income are related, okay? Do note that we only look at the how they're related, okay? Not causality, okay? It doesn't mean that when we have a regression model or a scatter plot where we show that, okay, how X and Y are related, it doesn't mean that X cause Y or Y cause X. It's possible that Z is driving X and Y, right? Or actually Y drive X. It's entirely possible. Running a simple regression doesn't tell you which cause what, okay? It's just a correlation. And probably the next question is how to establish causality, right? It's a rightful answer, right? Because what we run regression or we have a more complicated model of machine learning doesn't help you anything about causality, right? It can help you to establish how they're related in terms of prediction, right? Machine learning in that sense is help you to predict, right? You see this X, it predict Y, right? It's useful when you have a lot of prediction business decision model, right? Suppose an application would be say, okay, suppose you have a second-hand car, right? You want to sell the price and you don't know what price to sell, right? How do you do it? How can you set the price? The easiest thing to think about is you can look at the website, look at how other people are selling at different dimension, right? Because a second-hand car, right, we have many specifications for the car, right? How long you have driven it, right? What's the condition of that? And there are many parameters of the model, right? So in that case, you have to look at what are the prices have been transacted, right? And then see what are the reasonable price that involve a prediction model, right? Because we need not care about what drive what, right? We don't worry about, say, for example, in the causal model, you say, what if I wait one more year? What will the price drop? right? Then we know causality idea, right? But if we really care about what price I should set, what's the best prediction that regression model can do. But if you want to see how, say, how price change according to time, right? If you put the car there for 1 year, then you would involve a different kind of stuff, right? And to learn that, you will need much more elaborated econometrics method that will be way beyond the scope, and usually that will be reserved for a graduate level, PhD level analysis. So far we focus on prediction, okay? And the main idea we work is this X and Y diagram, right? The scatter plot when we learn the very end of the first chapter, right? Covariance and correlation. And then that is closely related to this graph. I mean, if you recall, if you try to fit this line, find the best fit by looking at the vertical distance, and you want to minimize the sum of the vertical distance, that's called the least square procedure, right? And turn out that if you, this is something you want to minimize that, okay? And there's a unique minimizer, okay? The one that turned out to be, there's only one, turned out to be like this, okay? And you do remember the first equation only says that the following very simple idea is the line would pass through the center of data, x bar, y bar. That is the first equation tells you. And the second equation tells you the very simple idea is this B is directly proportional to covariance, right? Because covariance divided by n or n minus 1 depends on what you want to look at, right? Or n minus 2, and that will be the power, right? And then the bottom is the variance, right? So it's a covariance over variance, right? So that would be the main thing, right? Because you expect the slope to be negative if covariance negative, right? So that is just the graphical like this, right? If this is the case, this is covariance positive, then the slope is positive, right? If this is negative, negative, right? If they are covariance 0, then you expect B to be 0 as well, right? And do note that what we talked about so far has no statistics, right? Remember what we do here, right? Where we run this regression at the very end of the last Wednesday, we calculate this. There's no statistics, right? Just math, right? This part, actually, least square method is done, or first invented by Gauss, a mathematician, right? And he actually doesn't care about statistics. Of course, he knows statistics, but this method is independent of statistics. Just the vertical line, vertical distance to the line, right? And minimize that, right? It's a simple, if you look at the math, right? I didn't do it, but if you try to track the math behind, is something like the contrast equation is just like multivariable calculus, right? So it's nothing really with the statistics, right? There's no probability, there's no random variable, and then probably the question is, right? In this model, right? We just pick the data point, right? There's no about sample idea here, okay? So now in order to go to sample, we have to talk about a model, okay? So far, so that's why we have what we call the classical assumption. Here is we will talk about probability or statistics, okay? Before that, we have no idea of that, just give the data, best fit, okay? And now we talk about data, right? We collect some sample there, then we have some assumption, and we'll show you that the method we described, the least square method, minimize the vertical distance, has a very nice property, and that's why everything goes very well, okay? So now we have to make the 4 classical assumptions, and you will see they're all very restrictive. And you may ask, why in the second semester you study this class, you will spend the whole semester for regression? The reason is you will be relaxing these 4 assumptions one by one, and at the end you have a very general model. Okay, so that is what you do if you do second course or econometrics, that you will be doing everything there, okay, one by one, by relaxing all of them. Okay, the first one is very simple. It's simply saying that what we call x and y are actually related in a linear way, right? We draw a line, then what we expect, there's a alpha and beta, you give you x, and there's y and there's an alpha there. So what does that mean? Let me draw a picture to explain what's going on there, because otherwise giving you this is not really the big thing. So the main thing is like this. Each observation you observe is generated by this process. Okay. What does that mean? I scatter plot x and y. Okay. For every x you give me, say the observation x1, right? Suppose I don't know where x1, but suppose x1 is here. Okay, suppose x1 is here. Okay. What y you would see, okay, will be alpha plus beta. This is alpha. Okay. And this is alpha plus beta x, right? If you learn math, that's what it means, right? That is the slope-intercept form, right? The slope is beta, right? Now, with this guy here, x1 is here, okay? What we assume the model now is, if you give me this x, okay, the y will be somewhere here, okay, but it will go up or down by epsilon. Okay, you will be later you will see you will around here on average. Okay, it can go up or down, but that is behind the model. Okay, and x and y are related in the linear form. Okay, of course there's assumption there. If this is wrong, then of course everything fails. But we assume behind that is linear. Okay, and probably we say okay, it's very restrictive. But later you will see when you learn a further class, you can relax it to say any polynomial, okay? And you run the regression, that's fine, okay? And you learn that from calculus, right? Any polynomial, okay, is a good approximation for any continuous differentiable function, right? As long as you think in the world is like continuous, polynomial is a good approximation. Of course, if you don't like that, I mean, there's more way. If there's discontinuous here and there's another way to do it, but it's not that restrictive. I mean, if you because you can allow your model is very general. So, but in the moment for concern is we know that x and y are related in linear way. We just don't know alpha and beta is. Okay, alpha and beta decided by the nature. We want to discover that. Okay, they relate, and epsilon I is something. What's that? Later you will see this part is probabilistic, probability there. Alpha and beta are number that we don't know. It's not probability. There's no probability. Alpha and beta is just something we don't know. Okay. Epsilon r is the stochastic term. This is a random variable there. Later we'll define in the fourth assumption. But it's epsilon I is the thing you can imagine is something is not in our model. We don't know what's that, right? In that case, say, for example, x is our education, y is our income, right? So suppose we say you study more, you have higher income, right? That is related in this way. And in that case, what's epsilon I there? Epsilon I are something is not education. Say maybe your EQ, right? Maybe your network, or maybe your luck, right? That would be the case, right? Or next Wednesday exam, right? Exam will depend with the y, depend on x is how much time you study, right? The more you study, then the higher your grade, right? And they're related linearly, right? And what happened to epsilon? Epsilon I is maybe your condition that you wake up on that day, right? You are tired, sleepy, or you sleep well, whether you sleep well. There's many things that is not an xi, okay? It's other factors, okay? In this simple linear regression, epsilon I is everything other than x, okay? So that, right? So that is the model, okay? So do note that alpha and beta are number that we don't know, okay? That is a constant that we don't know, okay? There's no property there, okay? In classical sense, okay? And epsilon I is random, okay? In the sense that there's so many things there is not control, it's not model there, okay? So that is the first model we said is aura. It's something that is not there. This is a model, okay? It's generated by this way, okay? The second one is very problematic, okay? What it said is xi are controlled by you, okay? You may say this is very problematic because unless we unless you are in the lab, you can control X, right? Otherwise, it's very difficult, right? Of course, in business case, it's fine because very often we want to discover how X costs Y, right? Is say you look at marketing campaign, you change different amount of money that you spend on advertising, then how it converts to sales, that's okay, right? And the example with education and income is not that easy, right? Because it's not ethical to say you have 10 years education, you have 5, you have 6, you cannot control, right? Because people make decisions, right? In that case, this guy is a little bit problematic, okay? And of course, there's a reason why you need to spend a whole semester to understand this part. But for our purpose, X is non-random, so basically it's you decide that part, okay? Or government decide that part, right? And that is useful in business decision, that's fine, right? Because very often we look at data is generated by your business choice, and you choose it, okay? So that's is not a big concern. But if you want to use regression on a data that is not controlled by you, there's a problem, right? Like education and income, right? People make their own decision to decide how much schooling they want to have, right? For that part, you need a more elaborate model. Okay? But that is out of the scope of our class. We just say, okay, this is given. Okay? And of course, these are all the idealized assumptions. Nothing in the world will satisfy that anyway. Right? And 3 is an easy model, easy idea, right? What it said is epsilon I 0 and epsilon I have sigma square. What does that mean? It means that, remember, epsilon I is what? Is the random factor, it's an error if the thing is not captured by X, right? So we say, on average, the impact of, say, the EQ or the luck on average is 0, right? Some people may have good luck, some have bad luck, but on average, generated by that, okay? And the variance is sigma square, so it doesn't change no matter what the xi is, okay? Of course, as I said, this part can be easily generalized in more general framework, but that will be not in a class. So it can be dispensed with 3 is very easily, okay? There are ways to dispense that, okay? So what do you mean by that is, okay? If you are willing to assume central limit theorem, right? Then error should be bell curve, right? So assumption 3 simply means the following. If you like, it does mean the following. You often see in the book is give X there, the distribution is like this. It's a bell curve, right? So most likely the data is here, very unlikely is around there, right? And if you have, say, X2 is here, then we say we have sigma square here. We also have the sigma square here, right? Which means that the variance is the same shape. Okay? And that's a technical term here. It's called homoscedasticity, right? But we don't know that term, but that's like, you know, when you go to the next semester, you learn that will be the term that be there, and then that can be realized relatively easily. That's not a big deal for this one. The only troublesome usually, very often, besides, of course, you relax this, and this one will also relax as well in advanced class. What it said is the random factor for different observation is 0, okay? And this part, when those people who study finance and accounting data, this is something that often violate, okay? For example, probably you agree, the stock price now and next 10 seconds, they are closely related, right? Because you can imagine that someone would come to buy the stock, right? If someone see the price goes up, right? They call momentum effect, right? It's like when you see people come in to buy it, then probably it's a good signal you come to buy as well, right? They're related. So that means that over time, things are related, right? So observation across time, covariance cannot be 0, right? So that means, right, this is the idea, right? Is the, say, the conjugation, right? It's the crisis, right? Financial crisis, right? The price, if one thing goes down, then goes down. So for a long time, right? So the long-term trend there, right? And that means that they're not zero, right? So that's why there's a course, if you study econometrics or statistics, it's called time series analysis. You will spend 1 semester to relax these assumptions. Okay. And the other related is where we have cross-sectional data. Even you observe observation within the same period of time, these I and J are different individuals, they may be related, right? Because, for example, if you collect data in CHK, right, and apparently people in CHK are related in some sense, right? They got the same culture there, right? Then it's likely that within CHK, people may behave similarly. People in, say, UST, right, behave similarly, right? Say, for example, you have the worldwide data. People in China may be similar. People in US may be very similar across themselves, right? Because there's a national education or culture that relate them, right? So these are the problem matter, right? Even cross-sectional data, the problem, okay? So that means that no matter you talk about time series data or cross-sectional data, and most of the time I'm not talking about the random sample, right? So with random sample, there's always no problem, right? But if there's not random sample, there's an issue, okay? And these are problems that you address when you go to higher level class. So they're all very restrictive, for sure, right? But just then you know that we need to make them to get out the basic result. And you learn that these are no problem. We less them, then there's no problem there. This is related to physics, right? We learn Newton's second law, right? Force is proportional to mass. Sorry, force for acceleration, right? And mass, right? F equal ma, right? Then you can relax that to relax the assumption. There's no friction, right? And the mass is changing, right? And changing direction. There's a lot of things you can do there, but we just keep the basic line first, okay? So if we are willing to make this 4 assumption, what does them bias, okay? And this bias, one important thing actually is also made by Gauss, who also do the least square, is what we call the Gauss-Markov theorem. That help us bias a very important step is if you're willing to make that 4 assumption, we will say the AB equation that we set, right, minimize the vertical distance, that's called A and B, is that formula, is actually the unbiased estimate of alpha and beta. What does that mean? It means we call what's unbiased. Unbiased means that we collect one sample and give A and B, and collect other one with A and B, and collect many, many of those. Average of these A, average of these B would be accurate. Okay, just to remind you, what does that mean? It means the following, graphically like this. So let me draw another diagram to show what I meant by that, okay? So we have, in reality, right, we say this is the model, right? This is the underlying true world, how data generate, okay? Of course, we don't know alpha and beta, right? The goal is to discover alpha and beta, right? Because we want to discover how X and Y are related in reality, right? And so what you're going to do is collect data, right? So you will try to look at data, maybe the data you collect in this way, this, right? Most likely you will fall beyond that, right? But suppose the data you get, right? You collect one sample, right? And once you collect one sample, you can run the regression, right? And maybe regression like this, right? And the regression like this will give you, this is the A, right? And this is the B, right? This is one case, right? It's very unlikely that A is the alpha, B is the beta, right? But doesn't matter. What we want is unbiased estimate. So what we mean is, suppose we have another data set, we collect them, okay? And it maybe end up like here, here, right? And the line may turn out fit it maybe like this, right? Then that gives you another A, right? Maybe to be safe, maybe A2 here, right? To let you know this is the first one, right? And we have another slope, which is B2 here, okay? We will have many of this, okay? Collect many data, right? And unbiased means that average of these A1, A2, A3, right? Every time you have a sample, we have an intercept, right? Average of this intercept will be alpha. If you do many of them, okay, on average, you got alpha. Average of this B will give you beta, okay? So that means that is the reason why we believe in science, right? Because one guy do a lab there, he get alpha and beta, fine. The other lab do alpha A and B, many labs in the world, every lab give me alpha and give me A and B, right? Average of all the labs in the world will tell me the alpha and beta, because average of A and average B give me the answer, right? So that's why how science progress, right? Because everyone discover some aspect of the world, right? Average of every of us will discover truth. That's ideal unbiased, right? So then at the end, we figure out what's alpha and beta. Okay. So that is the first thing. Why we make this assumption there, because when we do least square, okay, estimate, we calculate by the formula we told you, right? We also do the Excel last class, right? Very quickly we do that, right? And that is the unbiased estimate, okay? Not only that, okay, unbiased is the first good thing, okay? Of course, there also a second thing, okay? Of course, this is, the proof is a little bit weak here, but we say this is also the efficient estimator, right? Remember, we talk about efficiency, right? Among the unbiased estimator, one estimator more efficient, a smaller variance, right? It's accurate and also have a less range, right? So, and of course, we only can compare the one that's also linear, right? But it's not linear, it's not as good as it is, right? So that's why we talk about regression, right? Probably that's why you learn machine learning. Machine learning probably will tell you something more, but they're non-linear, okay? And regression tree, all this one are non-linear. But to be sure, if you focus on simple thing, linear estimator, right? Which means that why the estimation A and B is everything's linear, it's a nice, okay? So it's nice within something, we know how to do that, okay? That is called the blue, best linear and biased estimator. But anyway, in short, if you don't care about the formal definition, it simply said regression is good, okay? The least square is good, okay? And this is good on average correct, and it's also it's correct in the sense that it's the variation, the accuracy is the best among the thing we care, the simple way to estimate. Okay, so that is the thing you keep in your mind, because I'm not. I mean, this is the statement, so I'm not interested in asking you this anyway, right? Remember, for ANOVA and regression, I'm not interested in the test is asking you how to use the Excel output, right? Not the computation, not the theory aspect, right? But of course, I hope you to learn why we do it, because many of you probably would not be doing the second class of statistics, right? The regression is the maximum thing you're doing, right? So I hope that you would understand what's going on there, right? So finally, when you run the regression, as we done last time, right? We actually did that, right? So we want to have interpretation, right? That's the model there, right? And the A is the slope, so A is the intercept, right? So what does that mean? When X is 0, right? What is the value of Y, right? And usually this A is not useful unless X can be around 0, right? If X is not around 0, the extrapolation actually have no meaning, right? Suppose you say X is education, Y is income, right? A will be saying that people has no education. But in the world, in Hong Kong, many places in the world, we have compulsory education. So there's no one actually have no education anyway, right? So this number A will not be very meaningful, but it's there. The most meaningful thing is the B, which is we care the most, right? Because we want to take out how X and Y related. That is full B, right? So that is, the idea is like the slope, right? It's like on average, right? If X go by 1, Y will be changed by beta. So that's interpretation you need to know, okay? So do note that it doesn't mean that if we change X by 1, Y go by 1. That's another story there, right? It's just saying that if I compare two observation, one has higher X, Y expect this one to be higher by beta. It doesn't mean that you change X, Y change by that. That's a different story, okay? Because you may not be able to change X. Is that okay? Now we learn, for the rest, we learn something more fun, right? So far we learned how to come up with A and B. The next part is we've done with estimation, right? So A and B are point estimate for alpha and beta, right? Now, but we learned that from topic 4 and 5, we learned important thing is confidence level and hypothesis testing, right? So that's what we're doing for the rest of today, is to go over these concepts, right? And we estimate A and B, okay? The question is our estimate will be anything meaningful, right? Get some number there, right? We look at the data, we get A and B, right? But where we learn from our previous understanding, right? These are unbiased estimate, right? But is it different from 0, right? What's the interval there? That is very important, right? Right? Because if we don't know how, we just say B is 10, right? But the interval is so large, it can be too big or too small, which is meaningless, right? So we have to be meaningful. We have to come up with the confidence interval, and then we want to do. We also want to do the hypothesis testing to test whether the model is meaningful first, and then we go to the next step is, if I give you X, what's with the Y given by that equation? But we also need a confidence interval, right? So that would be the two things we want to do, right? First, we want to look at hypothesis testing and confidence interval for the A and B, and then we want to look at that when we use the model to predict what will be the interval there. So that's the two things that we will do. Okay, probably we do the first thing today. Second thing we left for the next class. Okay. But depends on how fast we're going. Seems like we can go faster than we expect. Okay, but let's see. So this era, okay, is the model, right? The first line is the model, right? The model we say Y is alpha plus beta xi equal to epsilon, that's error. Okay, this is the part. Epsilon I, okay? This, remember, epsilon I is the factor that is not captured by X, but contribute to Y, right? And we say that on average, this other factor on nets out each other on average is 0, right? Remember, the classical assumption we have is the expectation means on average, this is 0, the first one. The second one is this guy will be sigma squared. Okay. And the third one, of course, we said the covariance of right the unobserved or other factor between two observations are 0, right? So as you can see, the second point, which is this one, right? In this particular model, in fact, when we run regression, beside A and B, there's other parameter we make assumption there compared to least square is the sigma square, right? This is different from, we draw a line there, right? When we draw a line, this best fit is vertical distance. But now when we have the classical assumption of regression, we make an assumption. When we make the assumption like the first line, and we also make the assumption that the variance of the unknown factor is given by sigma square. Okay, of course, if you believe central limit theorem, your bell curve. Okay, we will make the assumption when we do we make this assumption when we do confidence interval and hyper testing. We assume normality. Okay, and of course, we assume the underlying epsilon follow the bell curve, so everything follow. But you can safely assume that it's also followed by central limit theorem. It's also a bell. Okay, there's two things there. Okay, the question is we want to estimate sigma square, right? Because the sigma square later will be eliminated. We tell us what should be the confidence interval or hypothesizing for A and B, right? Because A and B are random variable, right? Because depend on what data you draw, A and B will be different, right? Just remember this one. Just go back to this diagram, right? Depend on what data you get, right? A and B can be different. So A and B are random variable, okay? Alpha, beta, and sigma are parameter model, which is fixed, you don't know, okay? But you try to guess them by using A, B, and later you see S. That is trying to guess them, okay? They are random variable there, okay? So just go back here, okay? So we will define E, okay, will be defined in this way. Is the yi minus a minus bxi. What does that mean? Okay, this is the data you have. This is the model you got. What does that mean? Go back to here. This is called the SI. The EI, what is that? So you add, this is suppose the red one, okay? This is the y hat you got, right? And this is the height of this is the y, okay? Is the vertical distance, okay? It's the vertical distance of the point you get in the line you estimate. It's called the error, okay? Error, later you will see very soon, is a good estimate of residual. Okay, we try to use this distance to estimate the epsilon. Okay, it's very similar, right? Epsilon is this guy, right? And we use this height, which is E. Okay, later you see the variance of this guy, right? Because variance of epsilon is sigma square. Okay, and we use sample variance of this one, right? Which is called S square, will be an estimate of the sigma square, right? The sample variance of this EI will be an estimate of the sigma square, right? The variation of other factor in the model will be estimated by looking at how each data point is away from the line you estimate. Okay, so that is a little bit complicated, right? So just to make sure, this is called residual. Make sure that you know the term. This is called residual, right? And this is called error. And error, remember, error is just simply the general data. There's other factor not captured in the model. Okay, can be, say, your income is the Y, education is X. Other than that is your EQ, your luck, whatever thing you take into account that is not there, right? And that part is called the error. And the error, we assume, have the variance of sigma squared, right? Because everyone has different luck, right? And to estimate the sigma squared, how we do that is, suppose the data is the red one, right? We run the regression, we got the red line, right? And look at distance, the line to the data point, that give us the E, the error, the residuals, and we use the residual, look at sample variance of residual, that will give you the unbiased estimate of the sigma square. And that is the formula here. Let's check out the formula. That's the formula. Okay, you will see here, this is the, why it's not coming out there? Oh. So it's the E, right? And it's because the way we draw it, it must be the case E bar I is 0. So because pass through there, on average, up and down are the same. Okay. So that means that this is the sample variance, right? Because you will take EI minus 0 and square, right? So, and you may ask here why I divide by n minus 2, okay? The reason is this unbiased, okay? And the simplest reason, if you don't want to look at the math, is because we have x bar and y bar. We estimate to mean, right? So we lose some degree of freedom there. But of course, it can be proved, but I'm not going to prove it in our class. But there's a proof in the, I think in the slides there they prove it. The proof is rather complicated, so I don't want to tell you how to actually work it out. But you divide by n minus 2 will be the unbiased estimate. Okay, and that's S square is actually a good estimate for sigma square. So you can imagine, right? If the simplest thing is, if you can imagine, right? If everything follow the line, right? As this will be 0, right? S square is 0. Then we suggest that sigma square will be 0 as well, right? So it's not something too much crazy to imagine, right? And this is usually we call standard error estimate. I don't know why they call this term, but this is, take a square root of that term. It's called S. Okay? And later after break, you will see this is closely related to what we call hypothesis testing on the A and B. Okay, and if you want confidence interval of A and B, they'll be there. Okay, and then we tell you the formula after the break, right? It will be something like, just a hint. Okay, it will be something like after we can do the example that this, but of the break we talk about A will be this confidence interval if A look like this, right? And the formula will be, this is the hypothesis testing, okay? And this confidence interval A, and then similar to the B, the same. Okay? And then after that, we will tell you the how to work out the Excel. We tell you this one. Okay. That will be the plan of today. Okay. So in the meantime, so please the break of 15 minutes, so you can please do this one. If you have a question, please let me know. We'll come back in 15 minutes later. 通通嚟㗎，你好唔好啊？要求即係佢有其他係擺喺嗰度，嗰個就係但係佢話平均嗰啲其他嗰個關係係單位有其他人相關嘅，所有人平均起嚟嗰啲嘢都係。即係話你有好運嘅衰運，總嘅嚟講，呢個都係準確嘅。就運你係冇關係，我好運你冇運冇關係。三個模式俾你，就模式俾你啊嘛。係啊。咁考試咪就係 Excel 考試咪就係我就係考試嗰度考試。但係我覺得而家我哋其實都要呢啲個 sense 嘅，所以要大家考慮。我直接講啊！你問呢個佢哋藝術然後就講睇下邊啲問題。三前No is feeling of them that they say look at the day. I know you know. 啲手就喺上面比較好。係啊，即係我估到佢哋我即係個 character 拉人哋 character 我可以答你個火嗰啲即係我你交到我去答你交我即係交到嗰個你交到個地方但係交咗就冇得上。煲水答你喎，呢個係 access 我搞你咁嘅啫，我出去啲飛之類嘅。我哋被 comment 咁即係呢個解釋係咁啊！我想幫呢啲船最近最用嘅就係網都發現到有使用嘅，不過係咪專業嘅都好鬼用嘅。你話你解釋點解呢度答案好鬼用嘅 education 冇關係嗰啲我呢就係個啲你都係呢個問題，你要學翻呢個問題，所以你要講個 basic 嘅開頭嘅你啲問題，而家咁重要啊，我要解釋呢個問題，咁跟住你講到好大嘅。即係我要點樣解？係 office， 因為話咁你係咪成日你係有問題先會做事咧？冇問題，你問乜嘢咧？明白晒你嗰個啲問題，佢考慮你十開埋啲。我想講online spending， 我所謂對於我哋講緊嘢，佢話呢樣嘢啱，比較新鮮。你覺得呢個係我哋講嘅？喺呢度。咁如果咁啲講緊機關咧，都好大有啲嘢係問題，但係我哋你細嗰一條 N 細，你應該同到細啦，好大都係。呢個問題應該有緊防，我知道。佢張圖咧有 sample size 個問題嘅，你唔記得咗？記得睇翻。啲人話我驚。你要 define 個 margin error，如果你知道 N 大。 Oh, okay.
So I think this is not trivial. I think that will be important. So the question here is like, what are the relationship hypothesis testing and ANOVA regression in general? Okay. So so hypothesis testing is general idea that you have some idea about how the world works. You use the data to check whether what you think the world is right or wrong. Okay. You think, say, the sample mean is 3. Then use data to see whether it's 3 or not. Or you want to see whether, say, gender gap, right? You think men make more than women, for example. You want to check the data if that's the case or not, right? Or you think that people who do business school earn more than people who do economics, say, right? And then how can you do that, right? Look, collect data, right? And then you run what we see, then we're done, right? So that's hypothesis testing. It's a general idea that use the data to check what we think about the world is right or wrong. Okay, it's a very general thing. ANOVA is a special case of hypothesis testing. In particular, we want to see, say, one way ANOVA is saying that is different group have same mean or different mean, right? Because ANOVA is a variance, right? It's like we'll say, suppose we want to say, is the money made by, say, Chinese U graduate, Hong Kong U graduate, USD graduate, CTU graduate are all same or different? Then use ANOVA, right? Is to compare different group, do they have the same mean or not? A particular case, right? Look at means, right? Right? It doesn't include the look at the variance. I don't care about that, right? We just compare means, right? ANOVA is assuming different groups same mean, and then you compare the variance, and then we discover whether the same mean or not. Okay, that's the use F test, right? Because hypothesis testing with T test, set test, many test, and ANOVA is an F test, right? and particular case and compare different groups. Okay, that is ANOVA. And regression is not related to hypothesis ANOVA. Okay, regression is simply a study how X and Y are related, right? And you can say regression is an extension of the idea of ANOVA, right? Because ANOVA compared to a group, right? But now I don't look at the group. I look at how direct X and Y are related, right? Because group is categorical and X is a continuous or discrete random variable. X and Y are related, right? And later you will see very soon, once we estimate the regression line, right, we can do hypothesis testing on regression outcome A and B, right? We want to check if the intercept is different from 0 or slope different from 0, right? That's what we want to do. We require hypothesis testing. And later you also see that when regression, we can also do ANOVA. Seems to be crazy, but later you will see we can do something similar to ANOVA in regression. But let's wait until then, okay? But you can see three very distinct things, right? I mean, of course, you can say hypothesis testing include ANOVA, okay? And regression is a separate thing, a way to estimate things, okay? So I hope I made it clear, but if not, then just try to assignment and you see. Yes. Yes, we'll test whether slope or intercept is 0 or not. That is a hypothesis testing applied in regression. Okay. The answer, unfortunately, is no, because unless you tell me the way to disable your Bluetooth, the answer is unfortunately no, because also during the exam, I'm not sure you will use ChatGPT, then it defeats the purpose of the exam. So unfortunately, we have to go to environmental unfriendly way. I'm sorry about that. The deadline for the project, yeah, I think extended already. So we can check here. I think the deadline for assignment 4, assignment 3 or 4, I forgot. It's assignment, what did I say? Oh, deadline of project, yes. The project has been, where's the Dropbox there? Did I didn't put a Dropbox yet, right? Did I say extend? I think I extend, right? So I think I just put a Dropbox there. Okay, that's fine. Let me put the Dropbox here. The project Dropbox. I think I put it like the due date would be 8th. Okay, I have 10 for a day at the end of the day. Okay, so you can just you were there, so you can submit your what's one? Oh, doesn't matter. The marks is for me, not for you. Don't worry about it. What happened? Oh, okay. Oh, November. Oh, sorry. It should be December, right? It should be December 6th. Okay, yeah, December 6th. We give you 1 week more. Yeah, sorry. Regression. Again, regression is very simple. Let's go back to the idea there. Regression, draw a line. Regression is nothing but this thing. Dots are related to the line, right? So just to recall why I want to do that. So I think missed the whole point of our class is we want to study how things are related, right? We want to study cause and effect, of course, right? Or do prediction. There are two things why we want to do regression. We want to do prediction. I give the idea, right? Suppose you want to sell a car, then what price to charge? Look at how people in the market do. You run the regression. There's a prediction model, right? You want to predict, right? I think there's a famous case in Hong Kong history is someone do regression on horse racing and they make a lot of money of that. Yeah. And then I think that actually is a Chinese CHK professor, a STAT professor who did that and make a very nice regression model and make a lot of money. And of course, this case go to court because there's a guy who is a hospital expert who collaborate with the professor here, and they dispute how to separate the gain because they split the money. And anyway, but regression do make a lot of money, can be, right? And understand how things are related, right? Say drug dose and recovery time, advertising and sales, right? Because ANOVA only allow groupings, cannot tell you, ANOVA can only tell you they're different, but cannot quantify how they're related. So regression is a tool to quantify how things are related, okay? And that's regression. And we learned that how to draw a baseline, right? Is minimize the vertical distance, right? And the formula is this formula, right? And this is just the best fit line, right? Just a kindergarten exercise, right? Minimize the vertical distance. But the problem is we often collect data, right? And the thing is we want to discover A and B, right? In the real world, right? Because if you regression, right, we want to say the world work, you believe the world work in this way, right? So if you, on average, if you study one more year, you get beta more money, right? If you don't have education, you have alpha money. That's what we believe. And you think that luck on average have zero impact on everyone, on average, right? Some people got good luck, some people got bad luck. On average, it's zero. That's a model you believe. You want to discover what's alpha and beta, right? And then we tell you that the Gauss-Markov theorem tell you that that's a good one. We do the least square sum is a nice thing, okay? The way that we minimize the square is the A and the B we do is a good estimate, okay? But the new thing here is we have sigma here, okay? And we said that S squared, which is the sample variance of the residual, okay, will be the best guess, right? Once we know the sigma square, right, then we can have a lot of things to do, right? Because A and B are random variable, right? So we want to do hypothesis testing on A and B and confidence interval on A and B. Okay, that is the goal of today. Okay? If we have time, if you don't have time, we can relegate it to Wednesday. But don't worry, we will of course finish everything. Okay? Just to remind you that if you lose yourself in anything, that's okay. You can look at the video again. But the main thing is you have to grade yourself green, done. Okay? Because that will require for your assignment. And the very last thing, for our exam purpose, this is the part that I want you to know. Okay, this is the part that, same as ANOVA, what I want you to know for the exam purpose, you master this part, right? Because this part is summary of everything we've done, right? If you know how to do it, then we're done. Okay? If you forget about why this assumption here, there, that's okay. Okay? Because there's no need to remember every single detail, right? But this is the practical part, right? You need to know how to use it, right? Later you see the p-value or this kind of thing there. Because this is hypothesis testing. Right? This is the confidence interval, right? And these are the estimate, right? And you can see the ANOVA part is also there, right? But that will be something we talk about next class. Okay. Can you explain how the critical value for the PXL? Oh, I guess this question is like the assignment, right? So let me just do a very simple review. Okay. Say, suppose we do a simple case, we do one tail test. Okay. Mu equal to 3, right? And mu not equal to 3. Okay. And t-test means that I don't know the sigma square, right? Suppose I know the x bar is, I don't know, 5. Okay. I just make up some number, right? S square is, I don't know, 10. And n is like 16. I just make up some number there. So this is what we get, right? Suppose this is the case, right? I do the one tail test here. Sorry, it's two tail test because mu1 is not equal to, okay? And then what we're going to do is t, right? will be 3 minus 5 minus 3, right? And will be 10 over 16, take a square root, right? So let me do Excel, what is the number of that? Because I'm not a calculator, so I cannot really out of my head tell you the answer, right? The numerator is 2, the denominator is square root of 10 over 16, right? And the t will be this over this, right? So 2.52, right? So just go back to here, 2.52, right? So that's just use your calculator to calculate this one, okay? So you ask me the p value. How do you do it in the Excel, okay? So just always you start drawing the graph first, right? T to the 15, right? And minus 1. 0 is here. The bell curve is like this, right? And what we say, this is 2.52. What's p-value? P-value will be the significance level just to reject. It's 2 tail test, the 2 side, right? So basically just we'll have this area and this area, right? Symmetric, 2.52 here, right? So this area, right? How to calculate this area? This area is 1 minus the left area, right? So area is T this, right? T this. And then 2.52, right? 15. True, because this is the, and then take 1 minus, because I want to the right-hand side, right? And times 2. That's the answer. Okay, so that would be the 2 tail, right? If you need 1 tail, then you will be the other way. You don't need to multiply by 2, right? Depends on which side you're doing. Is that okay? I think we do it many times already. Okay. And some of you ask me when I do 2 sample tests, I only discuss 2 tail, but you can do 1 tail, the same idea there, right? There's nothing new there, right? Let's go back to the, is that okay? I mean, let me cancel it. Is that okay? I mean, if you, I mean, this class is a record, so in case you confuse, come back to here. Okay. I hope that's okay. Okay. Where can we find all the input? For example, check our lecture slides. I don't know what to say. What do you? Well, we didn't. Well, go to the lecture slides. But at the very end of each one, I have collect everything there, right? It's already all there, right? So I think it's already there. Oh, what is residual? Okay, I think that's a good question. So just go back to this, what we have. So remember, we say the orange. Okay, let me draw it again to say what is the. Okay. So let me talk about what is residual and thing. So if we believe this is our world, it's generated by X and Y are related by alpha and beta. Of course, the world's not so perfect that something is unknown, right? So that's why if there's no other factor, it will be a straight line, right? But the point is, in the real world, there's some other factor, right? Because education may be linearly related to your income, but there may be how beautiful you are, handsome you are, how lucky you are, other things as well affecting, right? So these epsilon are called error, right? Error. Okay. And suppose these are data, right? And if you collect data, okay, you are not going to pick up everything there, right? So maybe you're lucky, you pick up this red here, right? Suppose this is a red you pick up, right? And you pick this up, then you have the regression in this way, right? This is the regression line, right? Then this is your A, and the slope is your B, right? And this, the line, the point you get is called residual, right? And if you look at this residual, you look at the sample variance, give me this S squared. And this S squared will be a good estimate of this error variance, which is sigma square, right? The variance of this is called sigma square. Okay. And as we said, this will be a good unbiased estimate of sigma square. Okay. And basically give you us how good your line is, right? Because you can imagine, right? The bigger the sigma square, the bigger your S looks like, right? Or reverse one way or the other, right? That means that how good your regression line, right? That's why S square, or take a square root of that, we call the standard error estimate, is how good your line is, right? If S square is big, then your line is not so stable, right? Or you can think that your line is not very accurate, right? So that is how good your line is. Is that okay? I hope this makes it clear. Don't worry, you can keep asking questions, because when most of the questions you ask me is the thing that I stumble up on when I was a student like you. To grab the idea of regression, it takes a long journey. For me, it took me like 10 years to really understand what's going on. Okay, now I can say I understand what's going on, but probably for you the first time to learn it, it will be very hard. I mean, it took me like at least 1 semester or 2 semesters to really understand what's going on, because you learn regression many class, as I told you, right? When you go up the analysis, actually you learn different type of regression. By then you learn what do you mean by regression. Okay. For now, I think in your head it just try to learn some terminology, some basic understanding, then that's it. Okay. And it's not easy to master this one. It takes a long while for you to get it. Okay. But in short, it just drawing a line, right? To best fit the data, right? It's hard, as I told you, right? Because this is a preview of what you learn in the second class in statistics. But the main idea is, again, is you have many dots, you want to fit the line there, and that how the best fit is the vertical distance. That is the least square estimate. Okay. And you think it's hard because there's a lot of formula there, right? But I ask you to replicate the formula with the assignment, then you know what's going on there. Okay. And the new thing that beyond the line would be, we are saying that, okay, if we look at the data, which we will, right? Because we can't have everything there, right? We look at data, okay? If we're willing to make this assumption, the way we do minimize vertical distance is a great thing. Okay, we're willing to make some assumption of the model, how X and Y are related in the nature, in the actual world, then we can go further, right? Because without assumption, least square is the best we can do. There's nothing we can do further. So we make some assumption there, we can proceed to say more. Okay, so because we create new model and we have some structure of how other factor there, then we can say more things, right? Because once we estimate the alpha and beta by A and B, we want to say what A and B would be meaningful. By meaningful, is different from 0 or not, right? So to do that, we have to make some structure of the model. Like ANOVA, right? We assume there's normal distribution, right? Different group, the same variance, in order to proceed. Same goes on here, right? We have to make the same equal variance for each X, right? We make the same assumption with ANOVA. Each group have the same error 0, right? The variance is the same. So we actually make the same assumption with ANOVA. There's nothing new compared to ANOVA here, right? ANOVA same. If you recall, it's the same ANOVA, right? The only thing ANOVA here is X is either 0 or 1. right? I think it's a good that you feel it's hard because it's very hard. So don't feel bad if you don't get it. You can just ask question. Oh, Friday. That's great. The speed is okay. Okay, most of you can still follow, but as I said, this is not that easy, so it takes some time to digest because ANOVA regression is something new. I don't think everything is covered in the high school. So I think the thing that hypertesting is covered up until the high school, where if you do the M1. Yeah, extended. Yeah, project is already extended. Okay, I hope you're right. I think last time if someone says have an egg and some work in observatory, and I hope that is the right thing. Oh yeah, I think you have to be careful. I mean, drive when you drive. It's one of the first killer, I think, in the most dangerous thing when you drive. So that's why I don't drive at all, because I don't want to die by careless driving. Well, if you collect your own data, probably you should put your data in your submission, right? Otherwise, I'll ask you, right? Or you use your data source, you just write that down, right? The data I analyze based on there, or I collect by myself, right? That would be the thing. Exam similar assignment, yeah, I think it's very similar, right? I mean, it's similar in a sense because, well, it's a statistics application, so basically there's nothing very innovative in terms of way we can ask the question, right? Of course, we may ask in different way, but the point that we are asking is very similar, right? Just give you this data, we want to do hypertesting, we do estimation, we run ANOVA, we run regression, right? If you give you this follow certain distribution, what's the mean, what's the variance, what's the probability, right? If the data with the mean, variance, kurtosis, skewness. So that's, I think the question we're asking is outline, cost outline is very clear what we're asking, right? The test is going to follow that procedure, right? We're not going to deviate from that, right? English, Spanish, English, I guess. Ha ha ha. You can bring whatever you like as long as paper. Okay. Cannot share. Bring your own. Okay. Just like you go to your toilet, right? Bring your own toilet paper. You can't share toilet paper, right? Same. If you have a suicidal thought, please contact help. I mean, our exam is very simple, so it's 1 hour, right? So it's not going to be end of work when you fail, right? And if you do, because I think our final exam just worth 30%, right? Or 40, 35? What is the percentage? 35? So I think that means that if you is how much is it? I forgot. 40. So I guess given the other part is if you do the project, you do the assignment, even if you fail the test, I think you still pass the class. Okay, that's not a big deal. I think the passing mark is like 50 something or 60 something, right? But in general, no one get low. I mean, if you attend the test, I think usually you get at least half of it, right? The minimum case is 6. I think so far the minimum is 60, 70. So shouldn't be a big thing. So do remind you that if you're sick or have some special case, you have to let us know in advance. Otherwise, we consider it as a fail. Okay. So no makeup unless you get approval from us. Okay. So these are the problem that you will see in the assignment. I think the assignment is, I don't know whether tee up with the assignment yet, but I think the last assignment I don't think it's done there, but the assignment 5. Assignment 5 will be we'll be doing something like this as well.
Right? Just ask you to do some calculation. Okay. So assignment 5, we just ask you to do ANOVA and the regression. Just follow the green thing. Okay. So let me show you how we can calculate S, right? That's important, right?
So it's rather trivial, right? Because we calculate A is like this, B is like this, right? So your X and Y, you can calculate Y hat, right? Y hat is simply you have the dot here, right? You fit the line there, right? Y hat the line fitted one. E will be the vertical. That's how you calculate the E, right? You subtract this from this is the E, right? And you take the sample variance, you get the E S squared. And take the square root will be S. And average of this is 0. So that's
how we calculate, and you work on it in your assignment. Okay. We ask you to do the same operation, give the data, you do it. Okay. So ask the TA to upload as soon as possible. Because TA, he said he's very busy, so I don't know. But I mean, he has been very busy.
because, okay, to be fair, he is a PhD student, first year, so he is also studying like you. But I try to push him a little bit further, make sure that it's out. So as I said, it's unbiased. Okay. And actually same as ANOVA, right? ANOVA is X is follows some normal, but now regression, we say this is the model. So, but I'm not going to talk a little bit more, but I want your attention to that.
Okay. What we can say, I mean, this is it. I just stay without proving. You can check the proof there, but I just stay down. Okay. You can prove, okay, A is a random variable, right? Because A is the operation you do, right? Minimize over distance, right? Depends on what sample you're drawing, right? You look at the
graph I drawn here,
right? So if you draw the red one, this is the graph you have, right? So if you draw the later data, maybe you have either A and B, right? Suppose you got the data. If your data is like this, right?
Right? And probably you might fit, this is the best fit line, right? Can be something very weird,
right? And then you give different A, different B then, right?
So A and B can be something completely very different from alpha and beta, right? So go back to here is,
we can show A, we have this formula, okay? And let's make sense of that one, okay?
So let's look at this. The variance of intercept depends on two parts. This is the first part and this second part, okay? And the first part is rather simple,
right? If the data originally, right, the other factor epsilon square is the importance of the factor not X, like, right? It's the EQ, your log, your thing, right? If the sigma is very large, right, then your possible A will be much larger, right? You can imagine.
The idea is, look at this graph here, okay? If your data instead like this, much variation here, right? Then the potential slope you would intercept you draw will be much larger, right? So that is the main idea behind. And if you have more data, right, much higher n, this will be smaller, right?
The more data you have, the variation intercept will be much less. You can see from the picture, right? If n is very big, right, then this thing will be go to 0, right? Because you get all the data you got, right? Then you're done, right? So that's, you get more and more data. The intercept you got is exactly A, right?
The next part is something looks in your head will be a little bit crazy. What's that guy? What is this crazy thing there? right? This crazy thing doesn't seem to be very friendly, right? But let's look at the denominator, variance of x, right? You can imagine your data is very concentrated at x, right? Then it's possible it can be positive, negative a lot of time, right? But if x is very separated, right, it can't go negative that easily, right? So the variance is much smaller. So that is, I offer the explanation, but I'm not going to, you don't need that, right? But this is the formula I just tell you. And why I need this formula? Because this is, you see in the book, right? Or they don't prove it anyway, but this is the formula. You can show it. So if you are willing to assume that these other factors are for the bell curve, right? Which might be due to central limit theorem, which can be true, right? Because many things add together, right? Or these are minor factors add together, the bell curve. Then the A is also a bell curve, right? Of course, the center is here. We follow like this. Okay. That means that the standard error of A, which is like the square root of this guy, right? Why I need that? Because immediately we can do the t-test, right? With normal, with the no sigma, we replace by f, the t-test, right? And okay, we can do hypothesis testing. The same formula there. Nothing new, right? So let's see the example there. So we want to see whether the intercept is 0 or not, right? We just A, what we found minus 0, pick as A, right? And the only troublesome is n minus 2, okay? Because we estimate 2 mean this n minus 2 big. Usually n minus 1, but it's n minus 2. That's the only thing, right? There's nothing new compared to t-test, right? T-test is, right? It's the same. Okay. And the next thing is interval estimate, right? And we said already, this is our point estimate, right? Already, right? Because that is the least square estimate, right? And we said this the unbiased best, right? BLUE, best linear unbiased estimator. So this is our point estimate of A, right? Sorry, point estimate for alpha, right? And interval estimate of alpha is very simple, plus minus the t and denominator, right? Because that is what we learned, right? Remember, it's like this, right? If you recall, how you come from this is this plus minus t times this guy, right? We have seen many times already, right? That's how the two-tail test and the confidence interval estimate are almost very similar, right? In most of the time, it's like this, right? It's plus minus the critical value, right, times the denominator, right? We have seen that many times already. The same applies. Okay, you look at textbook, they just have this as formula. It's applied. Okay, and here is the example. Okay, that's what we do is to calculate the S, right? And you plug in the SA formula there, right? Which is, right? This is the S. This is this S, right? This is N, right? This is this guy, 55, right? And 10 is this guy, right? So we can calculate this guy. And t-test will be the A over the SA, right? And it's 1.779, right? And then you can do the critical value, right? Or you can do the p-value, okay? But let me tell you how you calculate this guy, right? So you calculate A is 3.9, right? Right? And S of A, we know is 2.199, right? And we calculate T will be just A over SA, right? Which is 1.779, right? The hypothesis testing will be just T, how many N we have is 1, 2, 3, 4, 5. N is 5, right? N minus 2 is 3, right? So it's T3, right? And then the bell curve here, right? Which is 0. We do a two-tail test always, right? Unless you have some special reason, you will do a two-tail, right? Unless you know there's some reason why you don't do a two-tail, right? But in general, you do a two-tail test. And what we're going to do is you want to see we have 1.779, right? You want to look at the critical value or p-value. So do the p-value first, right? P-value will be looking at this area times 2, right? So that will be T this, right? 1.779, 3, true, 1 minus 2 times. That's a p-value, right? Or if you want the critical value, which is 2.5% on both sides, right? So you want critical value, T3, right? Is you want this area add up is 5%, right? So there's 2.5 here, right? You can find this guy and take this guy or one way or the other, right? Suppose I find this guy, right? So on the right hand side, 2.5, left hand side is 97.5, right? So you do T dot inward on 975, 3, and get this guy. If you really want this guy, we're saying T inward on 0.25, 3. But one way or the other, right? Because one is negative, one is positive. So it doesn't really matter one form which one, right? And then the value, you can see a 3 point something. So you can't really reject it, right? So this model is rubbish. We get A and B, we calculate that much, okay? But turn out to be this A and B, this A, we can't distinguish from 0, right? Because you look at this guy, right? Critical value here, right? This critical value is 3 something. So 3.9 times this is SA, right? This guy is here, right? And this is here, right? So this is going to be including 0. So the intercept is basically useless, right? We can say it can be as low as -3, can be as big as 10. So it includes 0, right? So basically it's not very useful. But doesn't really matter anyway. Most of the time the intercept is not something we care. Right? Sometimes we care, but most of the time we don't, right? But that is the idea. So we talk about the slope in the next class, right? Together with Excel and also the ANOVA, and prediction. So there's something left to be done next class, but more or less you know what's going on for the rest. It's not something complicated. Okay, so I see you on Wednesday. So enjoy a typhoon break if there is someone tomorrow. So I see you. If you have any question, please feel free to ask. I stay around.有答案咩？
係聽日先得啦，我啲 level 你得19號先得啦，
係咯，個 TA 可能唔知道我哋 extend 嘅，我唔知喎，冇叫佢。
因為我見佢有2個 deadline，佢 PDF 嗰度寫15號，但係香港話寫19號，咁但佢已經有答我教。
我冇嘅 TA 唔到放，佢冇話俾我哋。
係即係咁，佢咪咁啱19號嘅 deadline？
係嗰19號 deadline，
即係都可以做交。
咁交做。
係佢做咗放答案。
咁你要問 TA 點解佢早放？唔關我事，我唔知喎。
考試係咪可以印多啲紙？
係印多啲紙
自己着數
係啦係啦。